facility, and Michael Beecher is not here. So I maybe have to propose it by myself. There's one machine on the planet called Luna, which is an accelerator underground. For some cross-section at low energies, they are so small you actually have to go underground to shield against cosmic rays and hadrons. And we are about to build the same facility or a similar facility, let's say, in Germany, in Dresden, where I'm located. And we have an underground lab, which is the deepest in Europe. It's not as deep as the Franzaso Mountain, which you have seen on the first slide, but it has enough shielding to get rid of all the hadrons. It's 110-meter water equivalent. And we have shown with some clever kind of anti-comp suppression veto, which we borrow from Luna for a second, that within a factor 3 to 5, we can reach the same kind of cross-sections like Luna. So in case very small ones are blended in the village of Luna, however, this machine can go not too far away from it. And in addition, it has, instead of 400 kV, which is the maximum energy of Luna, this will be a 5 MV machine. So this is the underground place. And this is the accelerator. So all this system, we are preparing for it. If nothing goes completely wrong, hopefully by the beginning of next year, we have this whole stuff installed underground, and it's supposed to be a user facility. So it's not for us, just for us to play. So if you have some proposals or some ideas what you want to measure, and you need low energies and low weak small cross sections, maybe come in touch with us, and maybe because there are so many people doing nuclear astrophysics, there can be some kind of common collaborations. So this was the advertising for something completely different. Okay, now back to double beta decay. That's me in my office thinking about the talk. I'll give you the idea of what is double beta decay, what the physics behind it. So this is a touch with us particle physics. So be aware of that. Then some very general issues to make you aware of how difficult it is to measure 10 to 25 years half-life. It's not straightforward. Some experiments, and you decide if I have some time, mention something on alternative modes, which means double electron capture. So this is all linked. The major importance for us is neutrino physics. So are neutrinos very special or only special? Well, we already know they are special. In a way, they are the only fundamental firmament which is not charged. And so therefore, and it's not a part of the nucleus, and so the only interaction field, if you ignore gravity for a second, is a weak interaction. Furthermore, as you have heard, weak interaction is maximal parity violating. So the only two states which are actually participating in weak interaction are left-handed neutrinos and right-handed antineutrinos. However, as I said, they are uncharged, and the question, in contrast to all the other parameters, is a neutrino its own antiparticle or not? Because we don't know, because if these two guys exist, which would make them similar to all the other elementary particles, they wouldn't interact in the weak interaction. That's why we nowadays call them sterile neutrinos. And then the neutrino would indeed be like all the other ones. But Ettore Majorana already came up about 70, 80 years ago with the idea that the neutrino could be its own antiparticle. So that's a left-handed and a right-handed state. If this is true, we violate total lepton number by 2 units. But this is a major step forward. I mean, when I was a student, I learned that the flavor and lepton numbers are conserved and total lepton number is conserved. But neutrino oscillations have already slaughtered the flavor lepton number conservation. However, violating total lepton number has much more profound implications on a lot of things, like the baryon asymmetry in the universe by leptogenesis, and making the neutrino its own antiparticle is a big step beyond the standard model, and it also needed to explain why neutrinos are so much lighter than all the other fundamental objects. So that's the idea. So what is double beta decay? As a word, it implies that single beta decay twice. Right? We have a nucleus decaying to its daughter, emitting 2 electrons and 2 antineutrinos. This is a standard model process. You see here 2 neutrons by chance decide to decay at the same time. As you can imagine, it's just very unlikely. So this will happen is on the level, and half-lives coming from this. Particle physics would call it a higher order process. The half-lives are in the ballpark of 10 to the 20 years. But this mode has been observed. However, the more exciting mode, the neutrinoless double beta decay, the nucleus decays into its daughter in 2 electrons without any emission of neutrinos at the one we are hunting for. Oh, okay, the animation doesn't work. So what will happen here? So the neutrino, the first, you can imagine it's a single atomic nucleus as a neutron decaying, emitting a right-handed antineutrino, which, like in beta decay, which in a magic way must be absorbed at the second neutron as a left-handed neutrino. So what you need is, the first thing you need, the neutrino must be an antineutrino, otherwise this can't work. So this is the first thing, and this is exactly what I mentioned on the previous slides. This is a Majorana particle. Neutrino is its own antiparticle. Furthermore, you have to match the helicity. If the neutrino would be massless, you have a pure right-handed antineutrino, a right-handed state a bit here, but you need a left-handed component as a second neutron. So if the neutrino is massless, this wouldn't occur even if it's a Majorana. However, if you give them the easiest way to match the helicities is actually giving a neutrino a non-vanishing rest mass, because then you have the left-handed component fixed at the first neutron, and this component will be absorbed at the second neutron. So the larger the neutrino mass, the larger this left-handed component, and the more likely is double beta decay. So our way of measuring is more like a seesaw, not like a beta decay where you look at an endpoint. We make our kind of mass measurements, the lighter the neutrino, less likely is double beta decay, and therefore the longer the half-life. On the other hand, if you see a half-life, you see the process, you can determine the neutrino mass. So these are the two essential things. To measure the neutrino mass via half-life measurement and double beta decay, and seeing it implies that neutrinos are their own antiparticle. And as I said, the measurements have half-lives, or expected half-lives, well beyond 10 to 25 years. Well, just here as an example, this is the isobar of A equals 76. You see all the guys on the left side are falling down by beta decay. So zinc to gallium, gallium to germanium 76. And the germanium 76 would love to decay to arsenic 76. However, the beta decay is forbidden by energy conservation. The ground state of arsenic 76 is higher than the germanium one. However, the second next neighbor, selenium 76, is lower. So this kind of transition is possible, or this kind, if you want to make it a tunneling or virtual transition here, it's up to you. But this kind of scenario, this triangle shape here, you need to see double beta decay. So you see the beta decay is blocked by energy conservation, but double beta decay is possible. So you all know the table of isotopes, the nice big books, and you go through all the isotopes you can find. You come up, there's only 35 candidates which have this privileged position here. So older people like me and Mike and Osvaldo, they remember proton decay times. That is easy, you can just buy 50,000 tons of water, it's cheap. And you look for proton decay. Here you have to rely on this 35 guys. There is no proton decay, no double beta decay in water. So this makes the experiments a little bit more expensive. Furthermore, this is a black box process. If you go in the particle physics region, any electron number violating process which converts two d quarks into u quarks into electrons can participate in double beta decay. So you see, theoretical particle physicists are quite clever people. There are a lot of things which you can imagine which could exist, and they could all contribute. There's actually a nice interplay with LHC at the moment, because LHC starts to restrict and constrain the existence of these objects. So the general scenario is you measure the half-life of the process, it's a decay. You have some phase space describing the final stage. You need a nuclear matrix element for describing the transition from the initial nucleus to the final one. And then you have a quantity of interest, the physics, which in my case I will focus on the light Majorana neutrino exchange. But as I said, there could be others. So if you then if you believe in the light Majorana neutrino exchange, the black box will look like this. You have a neutron here going into a proton. The left-handed W is the same, two W's. You have the couplings, two electrons in the final state, and in the middle you have the neutrino mass term. So the quantity epsilon becomes what we call the effective Majorana neutrino mass, and this is given by the total value of the summation over these terms here, which I explained to you on the next slide. The mixing matrix element squared linked to the electron and the neutrino mass eigenstates, and then this kind of equation is from the previous slide, the the epsilon will be just this term divided by the electron mass square. So there's a square dependence between half-life and neutrino mass. However, just to remind you, already 30 years ago, people have proven that if neutrinos double beta decay is observed at some order of perturbation theory, you can always draw a Feynman diagram which corresponds to a neutrino mass. So the statement is true that if you observe neutrinos double beta decay, that neutrinos are Majorana particles. However, if you can't exclude all the beyond standard model physics on the previous slide, then the real work will start, because you have to figure out how many percent is Majorana mass contributing to the decay rate when you have SUSY and double charge Higgs and others. This is a text question, but first let's observe it. So, but this statement will hold independently. Well, I think it's not a big secret anymore that the neutrinos mass and flavor eigenstates are not identical, and we have the same phenomenon which is known in the quark sector for decades, mainly the mixing. So we have a mixing matrix like the CKM matrix in the quark sector, and it's written down here. So it's a 3 by 3 mixing matrix, and you see this can be characterized by three angles, theta 1, 2, theta 1, 3, and theta 2, 3, and the complex phase, which is the quark sector responsible for CP violation, and the aim of high energy neutrino physics people maybe one day to discover CP violation in the lepton sector. However, if you think on the electric theory, typically in the phases, you have a lot of general complex phases, E to the I, whatever, and you can rotate or redefine the fields to get rid of them. However, the neutrino being its own antiparticle means you require that a charge conjugated field is identical to the normal field, which is somehow prohibiting the rotation of complex phases. So the net end result is, if you believe neutrinos are Majorana objects, you've got two more CP phases. And unfortunately, they are hard to tackle because they don't show up in oscillations. They only show up in double beta decay. We have no clue what the values are. So we have this matrix, which is very standard, and there's two additional phases coming from the Majorana character. Then this, if you write down this term which I showed you on the previous slide, you need the oscillation parameters coming here. Theta 1, 2, C means cosine, S means sine. Cosine theta 1, 2 square, cosine theta 1, 3 square, sine square, theta 1, 2, and so on. And you see here are the two complex phases. And you have the absolute value of that. So if the complex phases are -1, you have destructive interference in the worst case scenario. And this is completely different from single beta decay. First of all, single beta decay don't have these complex phases, and single beta decay is completely ignorant whether neutrinos are Dirac particles or Majorana particles. So in the past we were always asked, what do you want to do? A competition between beta and double beta. Nowadays it turns out actually you need both of them, because these are complementary measurements. So this is a shortcut here of our current knowledge, because you see here the oscillation results come in, so I have to at least tell you what we know. We know theta 1, 2, 3 is roughly about 45 degrees, it's not appearing here. We know theta 1, 3 is about 9 degrees, which is a major discovery in neutrino physics in the last 2 years. And we know theta 1, 2 is about 34 degrees. So this is the angles which go in here. And furthermore, the oscillation phenomenon, which is a different talk, which depends on the mass square difference of two objects, like m2 square minus m1 square, or m3 square minus m2 square. This is shown here. So we know that what we call the normal hierarchy, that the solar, to describe the solar neutrino problem and the reactor data, we need a splitting between m1 square and m2 square on the order of 7 times 10 to the minus 5 eV squared, or the difference of both numbers. And from atmospheric neutrinos and long baseline experiments, we know that the atmospheric, this can be explained as 2 times 10 to the minus 3 eV squared. However, we don't know the ordering. It could be the other way around, that the big splitting is on the bottom and the small splitting is on top. Or like here. So this one we call normal hierarchy, and this one we call the inverted hierarchy. And oscillations are not absolute mass measurements. That's why we don't know the offset with 0 here. So these are the question marks. Is this right or this? And this one or this one? This has keep the colors in mind because this has a profound effect on what we are supposed to see in double beta decay. So this is the same plot again. And what you see here is the expectation for double beta decay, depending on as a function of the lines of the neutrino mass. Meaning this one is M3 here, this one is M1 here. And then, so let's talk about the inverted one first. So this is a screen band here. That's what the inverted hierarchy with the current oscillation data would predict. You see, we are talking here in the region of 50 millielectron volts down to 10 millielectron volt neutrino masses. And I gave you here a kind of an idea what half-life, roughly, what half-life region this will correspond to. So the green band, if you really tackle this region here, you have to measure half-lives well beyond 10 to 26 years. Well, there is one observation from a Heidelberg group, which claim they have actually found double beta decay, and I think you have all heard about the last 10 years, a lot of noise about that. So if this would be right, actually 10 to 25 years would be the right number. So this would be up here, or in this band over there, already in tension with cosmology, and furthermore, this would imply that all materials are almost degenerate, though they have roughly the same mass and the tiny variations like fine structure and hyperfine structure. Because you need this small splitting for the oscillations. And as the normal hierarchy is actually realized in nature, you have this red band here. And then you see in the normal hierarchy, you can have this effect of absolute cancellation, even though neutrino masses are non-zero. And then you have to go beyond 10 to the 28 years. So this is a kind of a blue bullet points that will follow, spending most of the time on point 1. The claim here correct. This is basically the job of Görder phase 1 and EXO and Konstantin. Can we probe actually the green band? And if we haven't seen anything by down here, what about the red one? Can we do that? Depending on time, I will comment on that. Well, here's the shown up version. This is basically the academic plot from a paper from the Heidelberg group, showing you these bands. The actual position of the edges of the band depend on oscillation parameters, as is described here. So you see here sin theta 1, 3, cosine theta 1, 3 drops up, and theta 1, 2, cosine theta 1, 2, and so this is a cartoon from 2006, and there was nothing known about theta 1, 3, and the other one was even more a cartoon. And this is actually the real boundaries if you take the oscillation result, including their errors. And you see the band, this is inverted band, this will flatten off here because the solar mixing angle is not maximal. This is causing the region, that's why the green band is stopping here. But you see the red band with the current errors of theta 1, 2 and theta 1, 3. There's a severe range where there could be perfect cancellation and double beta decay, even without not mentioning neutrinos. As I mentioned before, beta decay measures something else. So this is this combination, so there's no complex phase, and beta decay simply ignores the character of the neutrino. This is a new experiment popping up called Catherine, which is supposed to start in 2015, which is trying to make beta decay tritium endpoint measurement down to 0.2. The current limit is 2 eV. And also cosmology is moving on. The latest data from the cosmic microwave background, and including baryon acoustic oscillations, people claim that the total sum of all neutrino masses is less than 0.23 eV. But in cosmology, I spoke with the project PI of Kaplan, there is still a little bit of room to go further. And you see that CME alone only makes a limit of about 0.8. So it's a baryon acoustic oscillation which hammers the mass down. Okay, so this was the introduction. So the search for the double beta decay, the joke is gone here because it's like a search for a needle in a haystack. So I had a picture of the needle in the haystack, and the needle was too large and the haystack too small. So this is basically the haystack. You have to find a needle. That's the thing you want to look for red decays. Just to give you an idea, this hopefully everybody can understand. If you go for the screen band, just as a back of the envelope calculation, what I'm talking about, 50 millielectron volt, if you want to do something else, just add zeros to everything. Orders of magnitude. This is a radioactive decay law, as you know it from your lecture, but under the assumption that the half-life is much longer than the measuring time. I think with 10 to the 25 years, it's a pretty fair statement. Well, if you want to measure this 50 millielectron volt, you have to measure 10 to the 26 to 10 to the 27 years. Okay, so for personal amusement, I mean, we don't ask for much, but 1 decay per year. I mean, otherwise it's really no fun. 1 decay per year. You need something, if you look at the equation, you need something like 10 to the 26 to 10 to the 27 source atoms. Now think about it. 1 mole of molybdenum 100, which is actually a double beta emitter. 1 mole of molybdenum 100 is 100 grams. So if you want to have, and 1 mole is 6 times 10 to the 23. So if you want to have 6 times 10 to the 26, you need 1000 moles, which means 100 kilograms. So even from the radioactive decay law, if you want to measure this region, you need 100 kilograms of the isotope. There's no way out. Otherwise, you don't. Maybe you have 1 event per century. But then I wouldn't do the experiment anymore. But this is a game to play, and then you only lose. You never have 100% abundance. You have maybe not 100% detection efficiency, and of course, you have disturbing events and background. But nevertheless, it's driven, these numbers are driven by the radioactive decay law. So, like in the first slide, what you have to do these experiments underground. There's no way, like also solar neutrinos and most of the neutrino business. So what do you actually observe? Well, if you measure the sum energy of the 2 electrons, it's actually pretty nice. You measure a peak at the Q value of the nuclear transition. So if you know the initial and final mass of the nuclei involved isotopies, you can determine the position of the neutrino peak. So that's shown here. It is a germanium 76 case. The peak is supposed to be at 2040 keV. However, in the 2 neutrino mode, like in beta decay in a similar way, because the neutrinos escape, you've got a continuous spectrum, which is shown here in yellow. The other one are more exotic decay modes, which have escaped. This equation you have seen. So from the experimental point of view, in the perfect world, the half-life sensitivity you can measure depends on the isotopical abundance, the detection efficiency, the mass, and the measuring time linearly. So isotopic abundance in the background limited case, this is shown here, for example, here the peak, and you see there as background. If you have a detector, you have always events all over the place. So we have a non-zero value here. And then the half-life sensitivity scales only with the square root of measuring time, and the other quantity coming in is the background level. This, of course, should be as small as possible. Furthermore, what matters, if you get this peak, the energy resolution, the width of the peak should be as good as possible, because it goes in here as well. So, because if you have only 2 or 3 events, you don't want to have them scattered over hundreds of keV, you will never find them. Because there's a 2 neutrino spectrum, but the half-lives are typically 6 orders of magnitude shorter. So all the events from here will move in here. So this is a kind of equation, but you see that the H stays in front, which means most of the current and future experiments, almost all, are isotopically enriched. That's the only way to increase your sensitivity quickly. Well, this is something, the master equation again. This is what you measure, that's what you want to know. We have a conversion factor, and this is the dark side of double beta decay, not the dark energy, the dark matter, but it's the dark side. So we were hoping that the phase spaces were actually determined pretty well enough, but now Franco Iacello and others came up, and we have recalculated phase spaces, so they have changed. Nuclear physics is a complex beast. Osvaldo is the expert, you should ask him about everything which is linked to the nuclear matrix element. But just to give you a feeling what's going on, for example, in the 2 neutrino decay mode, this is germanium 76, which I've mentioned before, going to selenium 76, it's a 0 plus 0 plus transition. For the normal mode, it's just 2 gamma tellers. So basically what you have to do is that you measure the BGT or the gamma teller strength from here to here, from here to here, you multiply those numbers, and then you sum up all the 1 plus transitions up to the Q value basically. 10 minutes or 1. Okay, Osvaldo, you have to do the job in the coffee break. And now it's stuck. That's not too good. So the experimental part. So these are the fantastic four because they have started data taking soon. So this is Gerda, must be because it's a German female first name. It's the only female. This is candles, it's burning already. This is Kamlan Sen, it's a massive object, and Exo must be the smart one. So just to go through everything, Kamlan Sen is a scintillator, 1,000 pounds of liquid scintillator. People have made it balloon. Because of time, I have to rush a bit, so they'll ask me for details later. But they have installed 400 kilogram enriched xenon 136, which is another double beta isotope. They haven't found anything, it's published here, and this is already putting tension on the claim of Glapter, which somehow has vanished as well, unfortunately due to this break on the machine. But they have a big hump here. This is probably coming from Fukushima, that's what they claim. It's not double decay, but it's a position where you have to look at. That's the EXO result. They don't see anything. This is a region of interest here between the red bands, and so their number comes up again with like a half-life of this, and EXO basically exclude that this bump in Kamlan Sen is really double beta decay. However, EXO is riding the wave in a way that they expect 4 events in the signal region. They only see 1. So they can make a very strong limit of any additional contribution like double beta decay. However, if this stays 1 and they expect 10, then they have to question their background for it. Anyhow, whatever you do in this conversion from xenon to the germanium half-life, there is already uncertainties in the matrix element. So the idea was to build Gerda using the old Heidelberg, Moscow, and ICHEX detectors, all germanium detectors which were used in the 90s, getting rid of all the material and putting the detectors in a kind of a liquid argon detector for cooling and shielding, having water around, and you can get the details here. This is located in the Prasaso underground lab. You see the detectors are on a fishing string, they are all isotopically enriched. You put them in here and you have several of these strings with the detectors. So, cut a long story short, this is the spectrum, and in the region of interest, we made for the first time in double beta decay because of the good energy resolution we put. A blind analysis, nobody looked in the data region and the peak region to make sure that we are not biased. The background, you see, is pretty flat, was estimated from here to here. From the other lines, you can determine whether there's something in here. So we made a prediction and the background model and everything before we ever looked in here. We made really a statement, okay, if there's no peak, then we should see so many events in this region. And after opening the box, you see here the blown up version and the normal version, there isn't really a peak. And this combined with the xenon data basically puts a strong tension or strongly disfavors the claim of Heidelberg from 2001. Most experiments, but these are preparing for phase 2. EXO has at least sometimes more data on paper and hopefully release them soon. So what the future? Because of this Magnificent 7, because of they should be all online in 2014 using different isotopes, which also have vanished somehow from my slides. And there's a lot of R&D projects going on. And the beauty of this field, I have to say, people are aware of the complexity of the problem. And if we're really forced to go to the red region, it can be that experimental approaches which we prefer now will not ever work anymore, and we have to do something else. So we have a healthy region, we have the flagships experiment, and still a lot of R&D experiments where people are looking at as well. So this is going on with wood. I skipped my own one, which is Cobra. It's on 24-fold forbidden beta decays for those of you who are interested in. Now it's stuck again. Okay, so that's what I mentioned before. This for measuring tackling the 50 millielectron volt band. These are the typical compiling matrix elements from different groups, including Osvaldo's group. You see there's a certain scattering due to the uncertainty what half-lives you have to measure to touch the top part of the green band. And as from the other academic plot I showed you before, even the lower edge here on the green band, which is shown here, depends on the value of theta 1, 2. And you see here, from here to here, from the current uncertainty to theta 1, 2, there's a factor of 2 if you think about the sensitivity on neutrino mass goes with the square root, you have to improve experimental parameters by a factor of 16. And we are already at the edge what you can do. So pretty much I would encourage you to measure either one to better. That's the basic message here. Just to give you a feeling for the other one, for the red one, there is no real proposal. This will be full-scale experiments. It will be very, very expensive. You need more precise data to really get the boundaries here. And things which you don't care about at the moment, basically will matter. For example, at this scale, you have to worry about solar neutrinos. You know, yesterday's discovery is today's signal, is tomorrow's background. Solar neutrino electron scattering will be a major deal when we work that out. Major deal for double beta decay, and maybe all detectors which are not able to decide to discriminate between 1 and 2 electrons will fail at that level, because boron A solar neutrinos covers all isotopes of interest, right? So on the level of 10 to the minus 7 counts per keV kilogram a year. This was something I'd skip. There are some ideas about resonance double electron capture on an isotope to an excited state, whether nature is providing us this kind of scenario which was proposed by Bernabeu and Bukula some 20, 30 years ago. We went through a strong campaign with penny traps. So this is an alternative mode if you're on the right side of the mass parabola. So you have something like double positron decay, double electron decay, or the mixed mode. And indeed we found a candidate which in principle has a 10 to 7 times enhancement in this resonance transition from its state to the excited state of the daughter, but it's gadolinium 152, but unfortunately it's gadolinium is doing alpha decay, so it's not really too promising. So let me summarize. I tried to explain the double beta decay is of central importance for neutrino physics. It's gold-plated to probe the fundamental character of neutrinos. I can't get rid of George W. I'm sorry about that. Interesting times at the moment because of LHC and double beta decay, TeV scale exploration of the different mechanisms. We have new experiments starting. I showed you xenon results and Burger. There's more building up. However, to go to 50 milli-electron volts requires hundreds of kilograms enriched materials, and this will be really expensive. And I encourage the nuclear structure people from this 11 isotope pairs. We basically should get all the nuclear structure information you need. So either one day I'm popping up here like at Hillary on Mount Everest claiming we have found double beta decay, or I look like this poor old thing that we maybe don't find. Thank you.
I want to say something a little bit about the possible rate of improvement of the cosmological stuff. Some of the masses, how much better you get over the next decade.
As you showed Lev Landau's plot, right, on cosmology. The point is, I mean, what cosmology typically measures omega nu h squared. You already have intrinsically the uncertainty of Hubble constant squared, right? So the point is that the Hubble constant determined from CMB, from Planck, is in a slight tension with the Hubble HST measurement of the Hubble constant. So there are some uncertainties. Furthermore, I have to ask Sean Hannes to make a new plot. There was always a plot which parameters in cosmologies are correlated to the neutrino masses. And there are some parameters like sigma 8, the kind of the light to better threshold kind of things in galaxy H, Hubble constant, and a few more. And they are now very reasonably precisely known, but nevertheless, people are maybe pushing it slightly too hard. There's always a tiny dependence there. And the correlation and systematic studies are the crucial, as we talked about systematics yesterday. I mean, this is a crucial part. And you have seen the sum of the masses from CMB alone is about 1 eV. Only the bionic acoustic oscillation hammer is the best fit very down to 0. So there is some room, but cosmology is of course making sure these stringent limits and boundaries on it. How good they can be at the end of the day, they claim a lot. They claim they can do much better in the future, but again, this model dependencies and correlation must be taken seriously to account. And I don't have seen this correlation plot of all the parameters with the neutrino masses for use data.
Mhm.
Let's see.
So who has the speaker?